Let's look at some examples of tail recursion. So here's your task. Figure out which of the 4 procedures defined below are tail recursive. For a recursive function to be tail recursive, what I mean is that all of the recursive calls are tail calls, and therefore the procedure will be executed in constant space. So which of the following procedures run in constant space? Take a look yourself, and then I'll go through the answers. Let's first look at length. Length defined here is not tail recursive. The final expression in the procedure definition is a tail context, but the sub-expressions of it aren't. So in particular, this if expression is not in a tail context. And that idea that the consequent and alternative sub-expressions of an if are in tail contexts only works if the whole if is in a tail context. So this is not either, which means that evaluating length here is going to require linear space in the length of S. Let's look at contains next. Contains is tail recursive because the recursive call to contains is in a tail context. This is a tail context because it's the last expression in a procedure definition, and this is a tail context because it's one of the second or third sub-expressions in an if expression that's in a tail context. And therefore, this is in a tail context too, and that's the recursive call. So contains will take in something that's linear size because S is a list, but the amount of additional space required for contains to be called is constant. How about has repeat? Well, has repeat has exactly the same structure as contains. So has repeat is a function that figures out whether S has any repeated elements, and it does so by calling contains. So the entire if expression, which is the body of this procedure, is in a tail context, which means this is in a tail context, which means this is too. So the whole thing runs in constant space. And by the way, when it calls contains, that's not a tail context, but since contains already just runs in constant space because it itself is tail recursive, we don't have to worry about that taking up a bunch of room. Finally, we have a procedure to compute the nth Fibonacci number. So let's see how this actually works. Fibiter takes the current Fibonacci number, which is Fibonacci number k, and if we're all the way up to the nth one, which is the one we're looking for, then we return current. Otherwise, we call Fibiter on the current plus the k minus 1 Fibonacci number. And we increment k when we do that. So starting out, we check and see if we're just looking for the first one, well then we return 0. Otherwise, we call Fibiter starting with the second Fibonacci number, which is 1. So this is a tail context, so this is a tail context. So far, so good. This whole thing is a tail context, and so that is. So this recursive call is fine. But the problem is that this sub-expression of a call expression is not a tail context. So this is not a tail call, and it is a recursive function call to fib. So this whole thing is not going to run in constant space because it makes a recursive call. Even though we have two mutually recursive functions, fib and fibiter, for them to run in constant space, both would have to make tail calls to each other. And in this case, we have something that's not a tail call. There's more work to be done. As soon as we figure out the k minus 1 Fibonacci number, we still have to combine it with current in order to finish. And then we have to call fibiter on that.